Today we're going to be talking about replacing lead acid batteries with PHI batteries. Oops, excuse me. So if you have not sat through any of our presentations before, this is really what we're all about. We're trying to accelerate the energy transition to renewables and sustainable sources. We are reimagining the power grid. Really, this is affecting all of us as the grid is failing all around the United States, especially places like California, Texas that have experienced, natural disasters and extreme weather events over the past few years. And we're building a resilient energy future, something that is dependent not only on single large source generators, but something that is dependent on distributed assets, meaning, customers have some level of control on their own power. And we're trying to do this in a way that delivers economic value. We're not asking people to sacrifice in order to make this possible. So in today's presentation, we're going to first talk about understanding lead acid batteries. So we're going to dive into the form factor and the composition of lead acid batteries. We're going to talk about troubleshooting them. So maybe you're having some issues with your lead batteries and perhaps you can avoid replacing them at all. So hopefully we can solve a couple of minor issues for you if that's what's going on, if that's why you're tuned in today. If not, we're going to talk about how, when, and why to replace your lead acid batteries and how to design your new PHI battery bank. As far as post-purchase, we are going to talk a little bit about installation techniques, advantages of PHI batteries, and then of course, frequently asked questions. I see your question about shelf life. We are going to get there, so just hang tight. All right, so battery chemistry and form factor. So when you're looking at a flooded battery, this is going to have, plates vertically inside of it, and it's going to have an electrolyte that's just kind of sloshing around. This is going to require watering so that you add water to the electrolyte. When you do this, you should also be checking the specific gravity. And if needed, if the specific gravity is not where it should be, you're going to need to perform an EQ charge. Now, EQ is short for equalization. This is something that should be happening automatically on your controller. You should have equalization charges programmed in to happen on a regular basis. But after you do that watering, you also want to perhaps EQ if it's needed to get that specific gravity level to where it should be. And when I talk about specific gravity, I'm talking about the specific gravity of the electrolyte. So you actually kind of pipe it out and test it. With a flooded battery, your life cycle is going to highly depend on environmental conditions. So these batteries are able to withstand quite a bit of charging and discharging abuse. I use the word abuse to describe anything out of spec for that battery. So if your, manufacturer tells you charge this guy at 12.8 volts regularly on float, and then EQ is 14.5 volts, if you miss those by a couple of tenths of a volt, this battery is not really going to show any visual, or any, outward facing signs of struggling. It's going to be okay with a little bit of abuse. But if it's operated at a extremely high temperature, extremely low temperature, cold weather, extremely hot weather, it's going to really show in terms of its life cycle. As you'll notice, a car battery that is, in a cold environment and it's just used like crazy, maybe left not fully charged, that is not going to last super long. Now we look at sealed batteries, and this is where the electrolyte is actually sealed inside of a cell. So often this is maybe wrapped into a cylindrical type of cell or something along these lines. But the electrolyte is not just sloshing around. So in this sealed type of battery, your life cycle is a little less dependent on environmental conditions and more dependent on charging and discharging characteristics. So what I mean by this is it is a little more sensitive as to how you treat it, how quickly you charge it, how quickly you discharge it, if it's left on half state of charge, all these type of things. I see your question about micro hydro. We're going to get to that a little bit about using charge controllers, but really not too much in today's presentation. So hold on till the end and then I'll be able to get to that in detail. We'll have plenty of time. So we make only lithium iron phosphate batteries. And I apologize for my low volume today. It's a little bit hard for me to talk too loudly, but thank you for bearing with me. Lithium iron phosphate really is a inherently safe chemistry. It is difficult to cause lithium iron phosphate batteries to catch on fire or, cause thermal runaway within the cells. There's no toxic elements contained within the batteries, and they're landfill safe. And all this, I would say, is due to their lack of cobalt. Cobalt is an extremely energy dense but very thermally unstable element. Lithium iron phosphate is the chemistry we use, and we only use cylindrical form factor. So cylindrical form factor is extremely durable. It lasts a long time. There's built-in short circuit protection due to the shape of the cell. I mean, just think about trying to short circuit this cell with another cell. It's impossible. Pouch cells are, on the other hand, a little less durable, more prone to swelling and puncture. And prismatic cells are great, but just a bit bulkier, did not really fit the form factor for our application. Just the sizing and specifications just were a bit off. And going back just to note that lithium iron phosphate requires no spacing, at least not from us, and no ventilation requirements as well. So this is a big advantage. If you have lead acid batteries and replacing them with lithium, you're going to have an easier time. Excuse me. All right. So troubleshooting lead acid. Let's see some common issues you might be having and what could be causing them. So if you're having a low battery cutout event, make sure to check your battery voltage and then recharge your battery. If your inverter has turned off, it could simply mean that your batteries are drained and your inverter has disconnected from the batteries to protect them. Your inverter could also be shut off because of an overcurrent event. Maybe you've drawn too much power and you simply need to turn the inverter off and then back on, or maybe there's a breaker that you need to flip back on. Your inverter also could be off because of overvoltage or reverse voltage. So basically this would mean you either hooked up a 24 volt battery to a 12 volt inverter, for example, or you hooked up your 12 volt battery backwards. Both of these things could fry components within your inverter. Now, the purpose of me talking about this is really because I see a lot of people that have an issue with batteries in an off-grid application and maybe or a mobile application, and maybe within 5 minutes they've jumped to the conclusion that they're just going to replace their batteries. It's got to be the battery. And I wanted to point out that Sometimes these issues are quite simple and can be fixed. So don't just jump to the conclusion of putting in a brand new battery bank. We wouldn't want that new battery bank to also have the same issue. So my guess is a lot of you are here today because you're having issues with a lead acid bank and you're looking to replace that. So hopefully this can help you understand possibly what those issues are. So potentially the lights are dimming or fluttering. Let's say your inverter is not shut off, that's working fine, but you're seeing your lights dim or just flicker off and on when you're powering a large load. So if this is happening under a large load, just for a quick second, the snap of a finger, then this can either indicate you've got a low quality non-UPS inverter if your lights are being powered through the inverter, so 120 volt lights, or if your lighting is direct current only, meaning it pulls right from the battery voltage, that means that your battery voltage is dropping under a load. A very large load, this is normal. But if you've got a very small load turning on and your battery bank voltage is dropping and the lights are dimming, it probably means that your battery bank is too small for that application. All right, so a couple more issues here. You may be seeing sulfation within your battery terminals here. So chances are if there's white powder around your terminals, that will be a result of sulfation. And if it's on your terminals, then it's also very likely to be internally within the plates of the battery. Now this is an example of really, really bad sulfation. If your sulfation issue is very minimal, you can actually remove small amounts of sulfation with a long EQ charge. So keep that in mind before just tossing the battery. One sign of sulfation is the battery may physically expand in size and swell or, deform in one way or another. This is basically just lead and sulfate combining on the plates of the batteries, and this happens because the battery is not fully charged. If you leave it in a 50% state of charge for an extended amount of time, or go through many, many charge cycles without reaching full, this can occur. So for example, undercharging, not having the battery fully charged, you may not have enough energy, which is understandable from your PV array. It may just be cloudy for a few days. But another possible thing is that it's cold in the winter and you have not enabled temperature compensation. So temperature compensation is going to push that charging voltage up when it's cold and down when it's hot. This is going to treat the battery as it needs to be treated. Now you may also have the issue of off-gassing. So if you're smelling, I hope you are not smelling sulfur, but if you're smelling something that's coming from your lead acid battery bank, first off, note that they're being overcharged and you should turn that, charging voltage down, or maybe in hot weather, maybe you've forgotten to enable temperature compensation, which is going to automatically turn that charging voltage down in low temperatures. So any excess energy will electrolyze the water in the electrolyte and cause this to kind of turn to gas. This hydrogen itself is not it's not toxic, but it's explosive if it's not vented. Now, severe overcharging, more than just a little bit too long of an EQ charge, severe overcharging is going to create hydrogen sulfide. This is not only explosive if not vented, but it's also toxic. So be careful of this. If you are seeing hydrogen or smelling hydrogen, or if your batteries aren't properly vented, lead acid batteries can explode. I see a raised hand. I sadly cannot unmute you right now, but if you pop your question into the question box, I will address it. You're not supposed to exceed, going back here, you're not supposed to exceed a 4% concentration of hydrogen before explosion is, possible. So that is something to keep in mind. Excuse me here. So moving on from troubleshooting, I want to talk a little bit about how, when, and why to replace your lead acid bank. So if those troubleshooting steps did not solve your problem, here is what will. So when should you replace your batteries? Well, maybe they have a reduced capacity. So this could look like, to you, it will look like reaching low battery cutout and having your inverter disconnect more frequently than before without increasing the amount of energy that you use from your batteries. Excuse me. This can also look like your voltage dropping significantly under a load. So if you turn on a large load and your voltage not only drops to 12.5 or 12, but all the way down to 11 or 10 volts, that is not normal. And your battery bank is likely having issues. That, or you have a loose connection in a wire somewhere. So when I talk about reduced capacity, let's define this with the manufacturer's warranty. So for one example, a Trojan battery will be considered defective only if it fails to deliver half or less of its published capacity during the warranty period of 2 years. So if you've owned the battery for 1 year and it delivers 60% of its rated capacity, that is still a good to go battery, at least as far as the manufacturer is concerned. Our warranty, on the other hand, is 80% of the rated capacity within a warranty period of 10 years. So here is how to check the capacity of your battery. So number one, you can do this, kind of estimate it manually by using a constant known load of lighting. Maybe you've got 10 100-watt light bulbs, and that equals 1,000 watts. And maybe you use that for 2 hours. So that's 2,000 watts for 2 hours. Excuse me, 1,000 watts for 2 hours is 2 kilowatt hours. So that's a simple calculation right there. But you'd also need to factor in some, efficiency of your inverter and wire losses there. You can also use a kilowatt meter. So this you just plug into your wall and then plug your loads into that. So you know exactly how much energy your load is using over time. It actually keeps track of that for you. Again, though, you'd need to factor in the efficiency of the inverter and the wire losses before it reaches that load. And my favorite is a shunt-based amp-hour meter. So something like the Victron BMV712 over here on the right, that is going to measure the amount of amp hours going in and out of your battery directly on the main negative wire of the battery bank. It's going to keep track of all the energy in or out over time and clearly show you how much of that rated capacity you are getting. Now, one thing I want to point out is although you can take your car battery to automotive AutoZone or automotive stores and have them test them for you, they're not testing the capacity. They're testing that battery's ability to start a car with cold cranking amps. So if you're using one of these types of tests, although helpful for car batteries, it's not going to be helpful in this scenario for capacity testing. So another reason you may want to replace an existing lead acid battery bank, maybe your loads have increased. One issue with lead acid batteries is you cannot expand on an existing bank. So if you've got a 5 battery bank installed in a customer's house and they add a electric washer dryer, and turns out they need 3 more batteries. Well, guess what? If those lead acid batteries are more than a few months old, there is no good way to add additional batteries to that bank. You simply will need to sell those batteries or recycle them or whatever and get a brand new bank of the correct size. So this is why there's such an advantage to PHI batteries is you can actually add to them over time, anytime in their life. And we specifically warranty for this, and we include language on how to do this in our warranty and spec documents. In addition, maybe your sunlight availability is becoming more limited and you're running your generator more. So lithium batteries can charge way faster than lead acid batteries. Lead acid, you're looking at C over 20, C over 10, maybe C over 5 if you're pushing them real hard. With lithium batteries, you're looking at C over 2, so you can charge these guys in 2 hours fully from zero. So that's going to allow you to turn your generator on, run it really, really hard, have full capacity for a short amount of time, charge those batteries fully, and then turn that generator off, and then coast through the night on your renewable energy, or not non-renewable stored energy. But regardless, it's going to increase your generator efficiency to run it for a shorter amount of time. So going along with that same thread, if you need to charge your battery bank faster, maybe you're adding a PV array, another string to your array, or a wind or hydro system. If this is going to cause you to increase the charge current beyond the manufacturer's limit, you're going to need to look into a different battery type. Maybe your customer simply has health and safety concerns about their lead acid bank. There are toxic components within flooded lead acid batteries, and you're exposed to them every time you do maintenance on them. So simplified batteries contain no toxic chemicals and they need no maintenance. As far as health and safety is concerned, let's look at a quick comparison of failure modes. So let's talk about what happens when a lead acid battery fails. A lead acid battery is going to off gas. It's going to maybe overheat, as Joe has pointed out. When you overcharge them, they can honestly just melt from the inside out. And overcharging can also cause hydrogen sulfate to be released, which is again toxic as well as explosive if not vented. Do not exceed 4% concentration of this, or you will have a major issue. So that is the main failure event of lead acid batteries. If you're lucky enough to just burn off all the electrolyte and destroy them that way, that is the best way to do it and the safest. But if you're not so lucky, you will have some sort of explosion or melting event. Now, lithium iron phosphate batteries are not the same as all lithium batteries. Lithium iron phosphate are much thermally stable, much more safe chemistry. So even if you do manage to force one of the cells into a thermal runaway event, it's very difficult for that cell to actually release heat quickly enough to affect the other cells in the bank. So we've actually tested this. The Underwriters Laboratory, also known as UL, has performed the 9540A tests on our products. And what it's revealed is that heating the batteries internally with forced heat from a wrap around a cell has actually forced the cell into thermal runaway purposefully to see what happens. And what happens is really that the battery cells directly surrounding the heated wrap is they will go into thermal runaway, and none of the other cells will really be affected by this. It doesn't spread. The fire does not spread to other cells. It doesn't cause a fire at all, really. It just goes into a self-sustaining heat mode and then kind of fizzles out over time. During this process, a very minimal amount of toxic gas, if any, is released, and it's not flammable. So what happens here is cylindrical cells have pressure-sensitive venting, so they will contain pressure as much as they can, and then if it becomes to a level where they cannot contain the pressure safely anymore without deformation, they will release that toxic gas vent to release that gas, and um, that is basically how lithium iron phosphate batteries experience a catastrophic event, right? That's a pretty boring catastrophe. So moving on to the actual replacement process, make sure to decommission and recycle your lead acid batteries properly. So this means wearing proper PPE, such as an acid-resistant apron, boots, gloves, everything made of rubber, a face shield, and a spill kit. I remember helping Native Renewables remove some lead acid batteries from a customer's home. They were still connected and still were basically sizzling and popping and leaking leaking electrolyte everywhere. So we had to go in full PPE and take care of these batteries. Long sleeves, long pants for sure. As you are getting rid of the batteries, lead acid batteries are highly recyclable. So you may be able to just take the battery back where you bought it. Check with, AutoZone. They always have some sort of deposit that you pay initially to get the battery, and then they give you that money back when you bring it back. You often will actually be paid to recycle your lead acid batteries. So keep that in mind. Don't just toss these things in the trash. They are highly toxic to the environment, and they are highly recyclable. So please dispose of these properly. One thing to keep in mind is removing these things, they are extremely heavy, and oftentimes you may need a forklift. So just keep that in mind. If you're not able to carry your batteries, you can call. A lot of our installers have experience with this. They have experience not only installing simplified batteries, but properly removing lead acid batteries and disposing of them in the proper manner. All right, designing your new PHI battery bank. So first things first, sizing is extremely important. As you are sizing a lead acid replacement, make sure to use our calculators on our website. We've got a quick calculator that basically just tells you how many, input loads you need to power, and this will spit out a number of PHI batteries you can use, or a lead acid replacement calculator. You can enter the lead acid battery model and quantity that you have, and it will explain how many simplified batteries you need to match that usable capacity. Now, it really is easy to size a lithium replacement for a lead acid bank. You have a higher charge and discharge rating with lithium than you did with your lead acid bank. So if you simply match the usable capacity, then you will always be able to power the same amount of loads or more at any one time. So let's look at an example. You've got a 400 amp hour lead acid battery bank, but you're only using 20% depth of discharge. That is an 80 amp hour battery, effectively. So our simplified batteries are 75 amp hours each. So only 1 to 2 batteries would be needed in that scenario. This is going to help you and your installer avoid examining spec sheets for hours. Now, another important point here is the installation. It's going to be much simpler because there's no ventilation or spacing requirements. So whatever you have in place, whatever enclosure you're using or mount, the lithium batteries are going to be probably much smaller in overall size, lighter weight, and they can fit closer together. So really, it should fit into whatever enclosure you already have. You can even mount our batteries sideways or on their face flat or back flat. As far as equipment compatibility, since you're replacing your batteries, make sure your charge controller or inverter have the right programming capabilities. So you want a low battery cutout of 48 volts for your low battery cutout. That's the minimum your battery should ever discharge to for 5 batteries. And on the high end, you want to program your absorb charge to end at 56 volts. You want to use two-stage no float on your inverter. Really, this is just in an effort to not waste grid electricity or generator power. Charge controllers, you can use three-stage. I would float at 54, again, absorb at 56. And if your controller, I've seen a lot of wind and hydro controllers that just have one single voltage that they charge the batteries at. If they just have one single voltage and do not have absorb, I would select float voltage as your voltage there. So 54 volts for a 48 volt battery, 27 volts for a 24 volt battery, or 13.5 for a 12 volt battery. One very important point here is sizing. So sizing should be C/2. We require you to have double the inverter's capacity in battery bank size. So if you've got an 8 kilowatt inverter, you're going to need 16 kilowatt hours in battery bank sizing. And that is a minimum, so you can always exceed that, but you cannot go under that, or you risk discharging and charging your batteries too quickly. One thing to consider is, does your charge controller or inverter manufacturer warranty for the use of that equipment with lithium batteries? And if not, you might consider replacing it with a Solarc or Sunny Island inverter. These are two new, more advanced inverters. If you do need a replacement, they have, high level of pairing and I'd say information sharing with our batteries. So therefore, you're able to actually upgrade to the newest model inverter as well as the newest model battery, and those two things can talk to each other. So there's a lot of benefits there, which we go into deeply in other trainings. As far as purchasing, all of our distributors can help you find a battery. If you need help finding a distributor or an installer, be sure to check out our Where to Buy map or contact our sales team. So as far as installation of 5 batteries, this is our 3.8 kilowatt hour battery. It's 86 pounds, and you want to make sure to wire it in parallel only. So parallel wiring is not the same as daisy chaining. So let's just skip forward here. This is what not to do, okay? Do not wire your battery bank the same way you had your lead acid bank. I know that daisy chaining is totally fine for most lead acid banks, but it is not okay for a lithium iron phosphate battery. It's going to cause imbalances. They're going to charge to different voltages. They're going to discharge at different amperages. They're not going to be well balanced. And for a battery that's going to last 10 years, you need to make sure this is very well balanced. We're not talking about a 2 to 5 year lifespan here like lead acid batteries. Do not wire the batteries in series, so only wiring them in parallel to a common bus point. So I'm talking individual cables from each battery to a combiner or even a terminal block like this. You can also slap some very thick, beefy bus bars on the terminals of the batteries. And what you're going to do then is drill holes in those bus bars so that they fit the batteries exactly. Now, we do sell bus bars made for 3 batteries, but we do not sell bus bars made for more than that. So you'd have to get something custom. Be sure to use a torque wrench and calibrate that wrench to 160 inch-pounds. So one thing to avoid here is using a socket wrench. You can actually over-tighten the terminals using that socket wrench and potentially strip the threads or even snap the metal terminal. The torque wrench really applies to all batteries, though. I wouldn't say it's specific to us. It's just a good thing to keep in mind. Don't use small cables. So we really recommend, most of our installers are using either 4 or 2 gauge cables for each individual battery, and they're using the same gauge, same size cable, same length cable for each battery. So you've got, going back to this photo, this battery is the farthest away from the combiner. These two are a little closer, so they have extra wire coiled here, so that the battery current is traveling through the same length of wire for each battery. That's how to create a well-balanced system right there. So as far as commissioning your new batteries, be sure to connect all batteries in parallel on the same bus, turn them all on before connecting them to the charging device. So what we have here is remembering that if you turn on just one battery and it's already connected to this charge controller, that charge controller or inverter might have a surge, a startup surge current. That might be a lot for one battery to handle, so it's always recommended to have some sort of a DC disconnect beyond the battery bank. Note that when you're first connecting the batteries, they're probably going to appear, come out of the box around 52 or even 53 volts. They're going to appear like they're fully charged. This is because the last thing that happens to them before they're shipped out is they get charged up to 20 to 30% state of charge. This is as high as we're allowed to charge them before they reach the customer. We're not allowed to ship batteries fully charged because of transportation safety rules. So one thing to keep in mind is even though this bank might look full on arrival, they are not full and they need an initial, full charge after installation. So don't just turn them on and then turn on the lights and leave the house. Make sure to initiate a charge at the customer's home before leaving that bank. Also remember that voltage is not always an accurate indicator of state of charge. So for example, if you've got some brand new batteries at 53 volts, but you know they arrived not full, and you've got an existing bank at 53 volts, but your monitoring equipment says it's full, do not connect those in parallel because it could cause a rush of current from one bank to the other. But as far as order of commissioning, be careful not to short the terminals, but again, turn on all the batteries first, then the disconnect to the charging source. Then once that charging source is connected to the batteries, then connected to the PV array. As far as inverters, if you don't have a charge controller, you can do the same thing with your inverter. Batteries on first, then the DC disconnect for the inverter, then the charging source for the inverter, and then finally, after they're charged, turn on the loads. As far as, let's see what's next here, our IQ program. So if you've already installed our batteries previously, make sure to check out our Elite IQ program. This is going to give you visibility to our customers directly. So our customers are able to access this map and search for an installer or distributor. We also use this map internally to send customers to essentially the nearest and best installer. So if you're appearing on this map, we have vetted you, we know you have installed our product successfully, and we're ready to refer customers directly to you. So if you're already installing our products and looking to drum up a bit more business, let us help you with that. Apply for our IQ program today. You're also eligible for cash back. So we have a $250 photo contest for the best install each month and $25 cash back per battery installed. These are things that only IQ installers are, eligible for. So here's our photo contest. If you submit a photo and it doesn't win, know that it's going to be entered into a rolling entry. So maybe you'll win next month. Photos of people and equipment, like this handsome guy, myself over here on the bottom right, are the best, of course, but if equipment is all you got, we will still take it. So if you are already installing our equipment, again, you can apply right here. It takes just a few minutes. Make sure to submit your installation photos. You only need one installation now to become qualified, and you'll simply submit your paperwork there and then do a quick intro phone call with yours truly. Thanks for sticking around. I'm going to go ahead and answer any questions. So if you haven't entered your questions into the Q&A bar, be sure to do so now. All right. Olaf, for a microhydro system, is there any problem using a PWM charge controller rather than an MPPT charge controller? There is no issue using a PWM charge controller with lithium batteries. As far as the efficiency is concerned, it's probably more efficient to use an MPPT. But then again, I don't have much experience with micro hydro, so all the props to you. I'd love to learn. Is there a shelf life on the Simplify 3.8 24-volt batteries? I purchased 6 in December and have not installed them yet, but the voltage has not changed since delivery 5 months ago. This is a great point. Lead-acid batteries will discharge, on their own 1 to 2% per month for an AGM and 10 to 15% per month for a flooded battery. Whereas lithium iron phosphate batteries discharge well under 1% per month each month. So if you've got them in a very hot, humid environment and they're, not enclosed in an enclosure, maybe they do discharge naturally 1% per month. And then they're, only have a shelf life of, 10 months or 12 months after delivery before you need to charge them up. That's really, really on the high side. I actually would say that more than likely they'll discharge less than 0.5% per month and they'd last over 2 years after delivery. But just to be safe, I would definitely check them and charge them every 6 months. So if you need a charger, feel free to contact us at the email on the screen, and we can hook you up and let you know where you can get a good charger for these while they're just sitting on your shelf for an extended period. All right, Joe, back to your common question of there's a fine line between 100% state of charge where the cells are balancing and the overvoltage disconnect. How do you set up your batteries to achieve optimal performance without experiencing the catastrophic disconnect? So this is great if your inverter has communication, but what if you run an older inverter without battery communication? So what Joe's talking about here is a lead acid battery will increase in voltage steadily as you charge it, kind of at the same rate, right? So maybe each hour it increases 0.2 of a volt and so on and so forth. With a lithium battery, lithium iron phosphate specifically, it's going to be very stable in the middle of that charge cycle. And then as you get to the end of the charge cycle, where you're very close to 56 volts, it's going to rapidly increase in voltage to hit that 56 volts. And if you charge it further, which you shouldn't do, it will rapidly increase even more. Very quickly, with very little energy input, it can go from 56 to 60 volts. So how do we prevent that inverter from disconnecting from high voltage? How do we prevent high voltage events? I'll let you in on a little secret, is that after 56 volts, there is still quite a bit of headroom in that battery. So it's not, it's not completely 100% jam-packed full at 56 volts. There is some headroom there so that if you happen to experience an event where the inverter, improperly sends a little bit of current after it's full to the batteries will be okay. They can handle a bit more than that. So really we are treating our batteries gently to prevent that terrible event from happening in the first place with the settings that we've picked out with that 56 volt absorb and 6-minute timer and 54 volt float. So we're already taking care of that. How do you determine state of charge of batteries before connecting them to the bank? Well, I would just say that know that they shipped from our facility at 30% state of charge and that they arrived to you between 20 and 30%. So knowing that they're between 20 and 30% is kind of as close as you're going to get without having communications or a battery monitor. In a Schneider setup, using a Schneider battery monitor will help a little bit in determining state of charge, especially if it syncs at the top of every charge cycle. If you're not able to get this battery monitor to sync at the top of every charge cycle, then I would recommend just replacing it with a Victron BMB. I hate to say that replacing it is your best option, but the Schneider battery monitor is just okay in our experience with lithium batteries, whereas the BMB is really designed to operate with lithium batteries. So the BMB 712 is ideal. Are you able to combine a 3.4 with a new 3.8? Yes, actually you can. So all of your batteries would be treated as 3.4s, and the 3.8, the brand new battery that you're installing, would have a warranty that is effectively the same length remaining as your other batteries have remaining. So if you have a 3-year-old bank of 3.4s and you add a new 3.8, that 3.8 is effectively going to have a 7-year warranty remaining. So that's something to keep in mind, and why you should act faster rather than later on installing new batteries to the bank. All right, thanks everybody for stopping by. I will see you next time.